Good afternoon, everyone. So thank you all for coming today. So our first speaker today is a Python core developer at Microsoft working on the faster CPython project. Over the past 5 years, he's made key contributions to Python speed and features, including helping design structural pattern matching in Python 3.10. So today he'll share about what they don't tell you about building a JIT compiler at CPython. So let's give it up for Brandt Bucher.
Hello, everybody. So my name is Brandt Bucher, and I'm going to be talking about the new JIT compiler that we have been working on for CPython. Now, I gave a talk last year that was called Building a JIT Compiler for CPython. And after giving that talk, I realized that there should be like a big red asterisk next to that, right? Because while my talk and a lot of other talks about JIT compilers over the years do touch on a lot of the really interesting parts of writing a JIT compiler, why you would want to write a JIT compiler and how they work at a fundamental level, I feel like they gloss over a lot of the stuff that I actually spend a lot of time doing when actually working on a JIT compiler. And there's a lot of stuff that I wish I had known when I first set out to do something like this. Plus, I just think it's really interesting. And so today I'm going to help clarify the asterisk and tell you what they don't tell you about building a JIT compiler for CPython, kind of a follow-up from last year. So before we get started, a little bit about me. I've been using Python for about 8 years, and I've been involved in core development for almost that entire time. For the last 4 years, I've been part of Microsoft's CPython performance engineering team. And the last 2 years specifically, I've been working on the JIT compiler that I'm going to talk about today. So let's talk about this team a little bit. You may have heard this referred to as the Faster CPython project. Our team collaborates with lots of people outside of Microsoft, including in the community. And we've had some really good results over the years, and the results are ongoing. So the first year that we actually started working on improving Python's performance, our results were landing in Python 3.11. And that was awesome. Python 3.11 was, on average, depending on your workload, about 25% faster than Python 3.10. You don't need to change your code. You just upgrade Python. Everything works. And in the years since, we've continued delivering these improvements pretty consistently over the years. Python 3.14, which is due out in October, is going to be about 8% faster than 3.13, again, with no code changes. And what this means is that in aggregate, in less than 4 years, Python has gotten about 50% faster. And this is kind of across the board. About 90% of our benchmarks, 93% of our benchmarks have improved in some way during this time, and almost half of them are over 50% faster. And just to kind of show you like what the upper end of this looks like, about 20% of our benchmarks are over 100% faster. And these aren't just like micro benchmarks that don't actually represent real workloads. These are real things that people are waiting on in CI, say, for things like Pylint. Pylint is over 100% faster versus 4 years ago. And all of this is without even enabling a JIT compiler yet. This is just all of the other stuff that our team has been doing since we've been taking kind of a holistic approach to improving Python performance. And so we're really proud of these results. We think that we've done a really good job of doing some changes that have a real meaningful impact, but they're in a way that can be supported by the community if needed. And honestly, this is what happens when companies fund Python core development. It's a really special thing. So with that out of the way, let's get to some background. So let's talk about duck typing. I am going to talk about my duck simulator here. So this is a function that basically takes an iterable of ducks and it loops over them. So for each one of these ducks, we're going to quack the duck and then print the sound that the duck makes. And we'll also add a feature so that if the duck echoes, then we will double the sound. Is my mic working okay? Cool. And so they can handle a class like this. So if we have our duck class, for example, this duck doesn't echo and its quack sounds like a quack. But it can also handle other classes, like say a rubber duck that squeaks instead of quacking, or maybe has some more complex logic in its quack method. So the way Python runs this duck simulator that I've written is by first kind of parsing it out and compiling it to bytecode. And it's not really important for you to, understand exactly what's happening here, but just to give you a rough idea of sort of how Python executes this code, I'm just going to very briefly walk through from top to bottom what happens when the Python bytecode interpreter executes this loop. So as many of us know, Python uses a stack-based virtual machine, and so I'm going to show this stack here on the right. So we start this loop with an iterable the iterator for our ducks on the stack, and the for-iter instruction will advance the iterator and push the result to the stack. Then we store the result in the fast local variable duck. On the next line, we're going to load the fast local variable duck, get its quack attribute, and call that. And then we're going to store the result in the sound fast local variable. Then we load the duck variable again, get its echo attribute, convert that to a Boolean, and branch on whether or not it's true. Assuming that it is true, we are going to load the sound fast local variable, load the sound fast local variable again, add them together with the binary op instruction, and then store the result in sound. Finally, we're going to load the print name out of the globals, load the fast local variable sound one more time, and then call print on sound, pop the result, and jump back to the top of the loop. So that's how Python executes this code. And that's the way it's done it basically since Python was first created. So what we started changing in 3.11 was by the introduction of something called specialized bytecode. And so you may notice that all of these operations are completely generic. Python doesn't have any type information available in the source because it's dynamically typed, which means that everything from iteration to calls to attribute loads needs to be dynamically resolved at runtime for whatever types we happen to encounter. But what Python has been doing since 3.11 is it's observed that, well, actually, even though the programs don't necessarily have static types compiled in, most programs actually are executing on the same types when they're running. For example, if we're always adding two strings together, we're probably going to continue adding strings together at that same site in the future, rather than integers or floats. And so what the Python interpreter does at runtime is it rewrites these bytecode instructions to have inline fast paths for some common cases. For example, iterating over a list, loading in a method off of an instance, calling a Python function with the exact number of arguments that it expects, loading attributes off of classes, and so on. And basically what this does is it profiles your program, and what you find is that after your program has run for some time, rather than having this generic bytecode that can handle kind of anything, you actually have bytecode that can still handle anything, but has inline fast paths for the shape of your actual objects and data structures and memory layout. So everything kind of from here on out is about the JIT compiler. None of this is actually enabled by default in any build of Python yet, but it builds upon the specializing interpreter, so I think it kind of naturally fits to view it as part of the same pipeline. So once we have our specialized bytecode, the next step is to convert it to micro-ops. Micro-ops are basically just smaller units of work within an individual bytecode instruction. So even these specialized bytecode instructions still do quite a bit of work, and so by breaking that work up, it allows us to optimize it a bit more aggressively. This translation step is completely automatic. So as part of actually, like when we define a bytecode instruction in the interpreter, as a natural effect of defining that bytecode instruction, the micro-op translation kind of falls out of that, and we're able to generate the tables to expand every bytecode instruction into its micro-op. So this translation step is machine generated and very, very fast. At this point, now that we have the micro-ops, we can optimize them. That's kind of the whole point of bringing it up in the first place. So what this allows us to do is basically by walking over this linear sequence of micro-ops and keeping track of the different types and values that we're observing, we can, say, take some instructions and turn them into more efficient versions that do the same work, but in a better way. Hey, there we go. Does the same work in maybe a better way. Or possibly even find instructions that are doing work that is entirely redundant and that we can prove we can remove without changing the semantics of the code that's being run. This is how Python 3.14's JIT, which is experimental and can be enabled if you choose to opt into it, would optimize this sequence of micro-ops for the example that I gave. In 3.15, though, we're set up to do some kind of more work on top of the optimizations that we've already introduced, and we'll probably be able to remove even more of this work and get something that's a little closer to this. So once we have this sequence of optimized micro-ops, then the next step is to translate this into machine code, because we actually want to be able to run this stuff. And so we take all of these micro-ops and we basically translate them one by one into a sequence of machine code that does the work of that micro-op. Now this step is really cool because we use a technique called copy and patch that basically means that, sort of like the micro-op translation for the specialized bytecode instructions, we don't actually need to handwrite the assembly that's being generated here. During the Python interpreter build process, when someone's compiling CPython itself, as part of that step, we will generate all of the templates that are used to expand these micro-ops into the equivalent machine code. And so that means that somebody who's, say, fixing a bug in the normal interpreter, as part of fixing the bug in the interpreter, they will actually also be fixing the same bug in the JIT, which is really, really neat, and it helps with maintainability and also lowers the barrier to entry to be working on a lot of this stuff. So kind of with that background out of the way, let's talk about a couple of different things that I feel like are sort of interesting parts of working on a JIT compiler that I don't see talked about a whole lot, and that I think are pretty interesting, especially in CPython's context. So the first thing that I want to talk about is region selection. So I kind of took it for granted that we had this sequence of micro-ops that we wanted to compile, but how did we get there in the first place? Really, the JIT compiler doesn't start with a sequence of micro-ops. It starts with a bunch of functions, and some of them are running, some of them aren't, and we have to decide what we're going to compile. So the questions really are, what do we want to compile? If something is only being run once or being run twice, maybe it's not worth compiling. But if something is being run constantly, then it's something that we will want to compile. Similarly, where do we want to compile it? If I have a function that I want to compile, do I want to compile it in isolation, or do I want to maybe inline it into some of its call sites and compile those instead? When do I want to compile it? So like we obviously want to compile things that are running a lot, but we don't want to compile them, say, immediately, because we may be compiling things that aren't actually going to run that much. But if we wait too long, then we may not actually have an opportunity to make the program any faster. And finally, why? Like, we only want to compile things if we know that we're going to make them more efficient. So if they're using really dynamic code patterns or doing weird things that we don't actually compile well, then it's probably not worth it. So one approach that you can take is compiling entire functions. And this is sometimes referred to as a method at a time or Methodjit. And it's kind of maps naturally to the way we think about compilers because it's the way a lot of ahead of time compilers work. So let's say that I decide I want to compile my simulate ducks function. I'm going to show the kind of original source here on the left and then what the JIT sees here on the right. The JIT will basically just compile that entire function wholesale. And we have some kind of opportunities for how we want to optimize this, say. So like if we observe that we are often calling the quack method of ducks, for instance, then we can choose to inline the quack method of ducks. We can say if the ducks class is the duck class, then inline the method there, otherwise make the call. And you can do this kind of as many times as you want. For example, if we have rubber ducks, we can inline that method as well. But you can see that it's sort of introducing a bit of complexity here because we have a fairly complex control flow graph, and we're not really getting rid of a whole lot of polymorphism in the kind of context of the entire loop. You can also do this for attributes as well. So for instance, with the duck.echo lookup down there, when we're deciding whether to double the sound, we can also kind of inline the cached attribute lookup on the class and do similar logic there. But again, all of these things are sort of adding incremental complexity, and it's not always super easy to reason about, especially for something that's running while you're compiling it. To give an example of this, let's say that I had compiled all of this code to handle iterating over a list of ducks. Well, that's fine, but what if then my function is called again, but with a generator of ducks? Like, let's say we have something like this. What do I do here? Do I recompile the code to handle lists and generators? Do I have a version of the code for lists and one for generators? What do I do in this case? And honestly, this just sort of makes the control flow even nastier. If you look at kind of how the generator advances versus how the for loop advances, you'll notice that they all kind of advance in lockstep. So it's fairly easy to reason about how the control flow goes from the generator to the for loop and back again. But this starts to get really hairy as soon as you have multiple yield points or control flow or nested loops. And it can kind of be fairly difficult to reason about, and it kind of creates an optimization barrier. And there are lots of places that things like this happen, for example, in async apps. So that's entire functions or a method at a time JIT. Another option that we have available to us, and the one that we currently use in CPython's JIT, is a tracing JIT, collecting linear traces by following the program's path of execution as it runs. So to kind of show how a tracing JIT would handle this, I can say, we can basically follow the program's execution. So we can say, okay, first we do the for loop there. Then we call the ducks quack method. Now, at this point, we can actually see where the program is going to go since we're listening to it as it's running. And we can see that, oh, we're actually calling the ducks quack method. And so we can, again, guard that the ducks class is duck and inline the method call just like that. Then we return from that, and now we're checking whether the echo attribute on the duck is true or false. But at this point, we have perfect type information. We've already checked that the ducks class is the duck class, and so we know that the echo attribute is going to be false, like it is there. So we can actually remove this check entirely, and all that's left to do is actually print this out. And you can see this is pretty efficient. If you have just a list of ducks, you're going to be doing kind of the bare minimum amount of work to actually just quack all those ducks. Of course, we also need to handle the case where there's something that's not one of our duck classes in the loop here. But the key thing is that we don't actually need to compile code to handle that. We can just say, okay, for anything else, go back to the main interpreter and let it handle whatever dynamic stuff is going on. So eventually, if I, say, have a couple of rubber ducks in this list, then I'm going to be hitting this else branch quite a bit. And it will get hot, basically. It will be basically worth compiling. So at that point, we can just begin tracing again. We can say, OK, let's execute that else in the interpreter. But again, let's listen to what the interpreter is doing. And so we can say, OK, well, now it looks like we are calling the quack method of a rubber duck. We can check the loud attribute, which is what's happening inside of that duck's quack method. And let's say that we have a rubber duck where the loud attribute is false. At that point, we just return the squeak and continue execution up above. Again, when we look up the echo attribute of the duck class, we know that it's going to be true. So we can remove that check and actually just optimize the resulting addition and remove it entirely. And again, what you're left with is just kind of the basic amount of work to execute this loop for either a duck or a rubber duck. And again, you can see here that we have kind of two checks here where if it's something other than the two classes that we can handle, that else down at the bottom, or if it's a loud rubber duck, which is that guard there kind of near the middle, then we go back to the interpreter. And maybe if we start to observe those in the future, then we can compile traces for those as well that kind of branch from the same tree. But the idea is that we don't actually compile anything that we haven't really seen or that we're not seeing very much. And that still keeps it so that we can have perfect type information flowing throughout. One downside of this approach is that you can notice we're actually compiling duplicates of some of the same code. So if you have very branchy code, you'll find that some things near the tail of those traces can be duplicated quite a bit. And there are ways of kind of reducing this, but it is one downside of this approach. So one other kind of way of choosing regions for JIT compilation is a technique called metatracing. I don't actually have a whole lot of time to cover this today, but just ask your LLM of choice about the first Futamura projection. And don't misspell it like me. It's not Futurama, it's Futamura. And if you got that joke, go find Mark Shannon and tell him you got it, because he said no one would get it. So that's region selection. All right, so we've decided what we want to compile. Let's compile it. Memory management is another kind of weird thing about JIT compilers, because they do really weird things with memory. So if you're a C programmer, you've worked with readable data before. It's basically you can declare an array of data and you can read it. You know, nothing too special there. We've also worked with readable and writable data. So I can, instead of having this constant array here, I can declare an array and then fill it with values, whatever I want. Again, this is very common to see in C code. If you need dynamic allocations, malloc and free are something that you typically learn early on in a C programming class. Again, nothing too exciting there. However, it's not often that we get to work with executable data. So this is where malloc and free just aren't good enough. If you try to execute the data given to you by malloc, it's not going to work. For this, you need to pull out the big guns, mmap and munmap, or however it's pronounced. Basically, this is meant for mapping files to memory, but it's also used to write JIT compilers for reasons that I can't explain or understand. But basically, if you know the right magic incantation to kind of whisper to this thing with all these secret flags and numbers and stuff, then you can get memory that is readable, writable, and executable. Now, one downside of this, and kind of just something that we have to deal with, is that we need to allocate at a minimum an entire page of memory, 4,096 bytes on most systems, but more on some systems. And so this means that even if we want 4 bytes of memory for our JIT code, we're still actually getting an entire page of memory, which is wasteful if we're not very careful about how we're managing it. So once we have this readable, writable, executable data, how do we actually start executing it, right? Well, C lets us do crazy things. So in C, I can just type def a function pointer. So this is a type def for a function pointer that takes an int and returns an int. And then I take my data, I cast it to my function pointer, and then I just call that. And that's how you get into some JIT code. It's weird, but it works. And so this is, again, if you're watching this and you're seeing this phrase executable data, that should kind of start sending alarm bells off in your head, right? This is kind of a scary thing. If you're a Rust programmer, this is what we call unsafe code. And so basically, this whole being able to write and execute data at the same time is a scary thing. At best, you shoot yourself in the foot. At worst, it's a major security vulnerability, because if you have data that can then modify the code and start executing arbitrary code, that's bad. So what a lot of modern systems enforce, and what is generally considered best practice, unless you're intentionally writing self-modifying code like some crazy JIT compilers are, is to first mmap some readable, writable data. You write in all your data, and then you reprotect the page as read execute. And so this will basically guarantee that the data is immutable while you're executing it, but then it still allows you to actually write it. And if you do need to modify the data later, you can flip-flop between the different permissions or do tricks with mapping multiple mappings to the same page and all sorts of weird things like that. And again, I've been showing all of kind of the POSIX APIs for this, but Windows has APIs that are pretty much analogous. They're called virtual alloc, virtual protect, and virtual free. And they work pretty much the same way. So that's memory management. Finally, I want to cover debugging and profiling. So there's kind of a couple different categories that I want to cover. The first one is Python profilers. So these are things like PDB or IPD, or sorry, these are things like the profile module or cProfile. So basically, when you're running a Python profiler, you want the JIT code to also be calling all of the same profiling hooks. For the time being, it's easier just to not JIT code that has profiling hooks installed. And this is kind of convenient the way that profiling is actually implemented in recent versions of Python. So when you turn on a profiler, basically we use the specializing adaptive interpreter to install those hooks. So where we would have this bytecode here normally, as soon as a profiler is installed, it gets specialized with specialized instrumented versions of many of those same instructions that fire the profiling events. And so that actually is convenient, because we can just tell the JIT that, hey, if you are tracing some code and you encounter one of these instrumented instructions that shows profiling is active, just stop the trace there and kind of let the interpreter handle that. And so that has kind of the nice effect of we're able to JIT the code that isn't being profiled. Let's say you're only enabling this stuff for a single function or a single module. We can still JIT everything else in the process, but we can just kind of leave that alone and not have to worry about it. This kind of related problem is, what if I'm already in JIT code and someone turns a profiler on? We need to get out of JIT code as quickly as possible if we don't actually have a way of handling these hooks. It's kind of hard to see here, but as part of this micro-op trace that I have, we have a handful of these validity checks that are inserted kind of just before known safe points. So anytime that we could re-enter Python code and have a profiler installed, we insert one of these validity checks that will basically check a single bit of state and say, oh, if this bit is set, I'm going to bail out of the JIT code and go back to the main interpreter. And so anytime a profiling function is installed, we set that bit, and it means that we don't actually execute any code that we shouldn't be executing. This same stuff is used to invalidate JIT code if, say, a class attribute is changed, or other kind of global events that break the optimizations that we're performing. Another thing that kind of naturally falls out of this is supporting sort of the weirder features of Python debuggers. So if you're currently in some JIT code and you've optimized the JIT code based on some kind of assumptions about the world. Let's say that somebody enters a PDB session and starts messing with stuff by changing types or setting attributes or mutating things or using the jump command to go to different spots. We don't want to have to handle all of this stuff in the JIT, and it's a major barrier to optimization if we do try to handle it. So what we'll do is actually, if some of these crazy events are taking place, we'll just set that same validity bit, and the JIT will just exit when that frame is resumed. The last category is native profilers and debuggers. So these would be things like perf or GDB, where you want to be able to inspect C code. And if there are JIT frames on the stack, you need to be able to unwind through them and mess with them. The short answer is it's really, really complicated. And so there are lots of these tools. They all work differently on different platforms, and they all have their own APIs for actually registering debug info in different formats with different tools. So we're kind of aware of what we need to do. It's just sort of figuring out what the best way to do that is. We're trying to figure out, like, what tools do we want to support? Like, what's the most important features? Like, do people need to be able to actually run GDB in JIT frames, or is it just enough to be able to unwind through them and get to the stuff that's higher up the stack? And we also want to find a way to do this in a way that's maintainable and also doesn't slow the JIT down too much, as it's kind of generating all of this kind of crazy Baroque debugging information. Pablo Galindo has been a great help with a lot of this stuff, and I'm sure we have a lot of battles ahead of us, but this is something we're aware of. It's just something that's also pretty hard. So looking forward, Python 3.13 is the latest stable version. So you can build a JIT compiler for it if you would like to build your own Python interpreter. If you do that, you can just configure with the flag enable experimental JIT, and that will build a JIT for you. If you have Python 3.14, which is just out in beta a couple of weeks ago, you're in luck because the official macOS and Windows release binaries have a JIT built in, but it's disabled by default. So if you set the Python JIT environment variable, you can try it out for yourself. We don't recommend it for production use or anything like that, but we'd love to hear your stories of whether it's speeding up your code dramatically, slowing it down dramatically maybe, or if you encounter any bugs or crashes or things like that. Like, that's exactly what this sort of off by default phase is for. And of course, if you're on other platforms or you're getting your Python interpreter not from the official release binaries, you can still build your own Python interpreter with the enable experimental JIT flag. Looking forward, Python 3.15 is now in pre-alpha, and we have a couple of different lines of work. So as I mentioned before, we're looking into supporting stack unwinding in the JIT compiler for native profilers and debuggers. We are also interested in making the JIT thread safe. It's currently incompatible with free threading. We think that's fixable. It's going to take a little bit of work, and there's kind of a long tail of figuring out what optimizations are actually still safe to do in a free threaded environment. But it's something that we're definitely interested in doing during this time frame. Both of these things are areas where they are way outside of my domain of expertise. So, like, if you have experience or expertise in these areas and you want to help out, please reach out to me because, or reach out on these issues, because we could certainly use it. And that's in addition to, of course, a whole lot of ongoing performance work as well. But the key thing to remember here is that, like, fast progress and these larger projects will always depend on, like, the availability of resources. So if you want to read up a little bit more and get some more information, PEP 659 is all about the specializing adaptive interpreter. We also have PEP 744, which is all about JIT compilation. If you like watching things rather than reading things, then I've spoken at the last couple of PyCons. You can watch my talk inside the CPython 3.11's new specializing adaptive interpreter from 2 years ago, or last year, my talk about building a JIT compiler for CPython. If you're curious about how we're actually, like, generating the machine code that makes this stuff run, I really enjoyed putting this talk together, and I think the technique is really cool and fun. But other than that, that's it. Thank you very much for coming out. My name's Brandt Bucher. I'm at Brandt Bucher on GitHub and Python Discord. You can also reach me at brand@python.org. Thank you.